Hey, good afternoon, everyone. Welcome to welcome to lecture 32 of BMS 300. We will wrap up with the cardiovascular system today. But before we get into the material, I just wanted to make a couple of general comments on the overall performance in the first two exams. So it looks like most of you are doing pretty well, right? So I looked at everyone who got 60% and above, right? So both exam 1 and 2, and all of their scores is an average of 80%, right? So if you're passing the class, you're doing pretty well, right? But when I looked at the remaining around 30%, the average was around 49, right? So what I have to say is there's hope, right? Even if your highest score in the first two exams was a 30%, right? So that's 30% you can drop. You have to carry it on to the next exam. Even if your highest score was 30%, there is still time to, if you were to score an average of around 80 in the remaining exams, we have exam 3, 4, and the final, you can get around 75% overall and pass the class, right? So, in order to do that, you'll have to start now, right? And so please, I will follow up with me. I'll send you an email saying what are the next steps we can do. If you did really well, don't expect an email from me right now, right? I'm just trying to focus on the 30% and get them to do better. So we'll come up with a plan starting this week, which you can start working on, and then we'll follow up on a weekly basis, right, to make sure that you're keeping track of the material. And if you didn't do well in exam 1 and 2, that is not material you can ignore, right? Because it is going to show up on the final, and you will see how these concepts are integrated, right? So just heads up on that. So look for an email from me, and if you just aren't happy with your performance, if you think getting 70 isn't enough, you want to do better, come and talk to me, and we'll come up with a plan, right? So with that, let's get into an overview of today's material. So we're going to start with the pressure volume loop, and we'll see how this pressure volume loop is constructed. This will be based on the steps in the cardiac cycle. We talked about the cardiac cycle on Friday. We see how it starts with electrical activity followed by mechanical activity of the heart. Right? So we'll see how the pressure volume loop is constructed. And the main take-home message in the pressure volume loop is that we'll see how the contractility or the ability of the heart to produce force is influenced by the muscle length. Okay, so that's what I want you to take home from the pressure volume loop. And then we'll move on to factors influencing cardiac performance. And in this regard, we'll talk about what do you mean by cardiac output, and this is the amount of blood pumped by the heart in a minute. Right? And this is depending on two factors. One is the volume of blood pumped per beat, and the number of beats per minute. Right? That's the number of beats per minute is the heart rate. So we'll see how the heart rate can be controlled by the autonomic nervous system. We'll see what happens during sympathetic versus parasympathetic stimulation. And then finally, we'll talk about how blood flow is taking place through the various vessels, and how the blood pressure is going to change as it goes from one type of vessel to the other. Right? So in that regard, we'll go through these 4 different graphs here, and you'll understand how the blood flow will change from one vessel to the other depending on the changes in pressure as well. So let's see how the pressure volume loop is constructed. So in the graph on the left hand side, you notice that on the y-axis we have the ventricular pressure shown, and right below that you have the blood volume indicated as well. So this is the volume of blood in the ventricle. We'll see how that changes in respect to time, shown on the x-axis, and we'll also see how the ventricular pressure changes with respect to time. So that's what is happening on the left-hand side of the screen. On the right-hand side, you will see how a pressure volume loop can be generated using the information on the left-hand panel. So the pressure volume loop, you have the ventricular pressure on the y-axis, and on the x-axis you have the blood volume. And the one thing which is missing in the pressure volume loop is the time scale, right? You don't see changes in respect to time. In fact, it'll just be a loop which goes around over and over again. So we're going to start with the systole, right? Systole is where you have the contraction of the ventricles, and systole is going to be triggered by calcium entering into the cytoplasm. And when calcium comes in, you have actin-myosin interaction that causes pressure generation, and then the ventricles will contract. And what triggers this calcium release would be the QRS complex in the electrocardiogram. So that is referring to the ventricular depolarization. Now the first part of the systole is going to be the isovolumic contraction. Notice here that the ventricular pressure is increasing rapidly, but the volume has no change at all. Now the reason why the ventricular volume is not changing despite increasing pressure is because two valves are closed. Do you remember what the name of those two valves are? Atrioventricular valve, very good. And the other one is? It leads to the aorta.
Oh, is it?
Aortic valve, right? So both of these valves are closed, and that's why you don't have a change in the ventricular volume, right? And so the question is, why are these two valves closed? Now the reason why these two valves are closed is that the ventricular pressure is higher than the atrial pressure, but it is still lower than the aortic pressure. And so once the ventricular pressure exceeds the aortic pressure at this point, it leads to the ejection phase, right? But before that, let me just go to the right-hand panel. Notice that the isovolumic contraction is shown here just by a straight line. There's no change in volume, only the pressure is increasing, right? And so the ejection phase starts once the ventricular pressure exceeds the aortic pressure, and see that pressure is gradually increasing. Simultaneously, the ventricular volume is gradually decreasing because blood is being pumped out of the ventricles. Coming back to the right-hand panel, notice that the ventricular volume is decreasing as the pressure increases, and you eventually reach a point where the ventricular pressure is no longer increasing but starting to gradually decrease. And the reason why it's gradually decreasing is because the T wave took place and there is ventricular repolarization. And as a result, when you come back to the right-hand panel, notice that there's calcium uptake following the T wave, and then that will lead to the ventricular relaxation. Now the first part of the ventricular relaxation is an isovolumic relaxation. Notice that the pressure drops, but there's no change in volume. And again, the aortic valve is closed now because the ventricular pressure drops below the aortic pressure, and the ventricular pressure is still higher than the atrial pressure, so even the atrioventricular valve is closed as well. But as the ventricular pressure drops below the atrial pressure, the AV valve opens, and then you have the ventricular filling. And this ventricular filling is happening by passive mechanisms, right? It's just moving from a region of higher pressure to a region of lower pressure. And back to the PV loop, notice that the volume is gradually increasing, and that's how a single loop is constructed. Any questions at all, folks, on how the pressure volume loop is constructed? We talked about what happens on the left-hand panel in detail on Friday, and now we just see how the PV loop is constructed based on that. Are we good? Okay. Now there are a couple of things I want to point out to you. First one is the peak pressure, which is generated by the ventricles, right? We see that the peak pressure is denoted in both panels. And then I want to draw your attention to the end diastolic volume, abbreviated as EDV. This is the maximum volume of blood in the ventricles at the end of diastole. So once the ventricle is completely relaxed and it's filled with blood, at maximum volume is the end diastolic volume. And then the ventricle is going to contract during systole, and it's going to eject as much blood as it can, and that leads to the end systolic volume. So systole is the contraction phase of the heart. At the end of systole, that's the end systolic volume. Now if you subtract these two volumes, you come up with this value known as stroke volume, right? So you see the end systolic volume is shown here, end diastolic volume is shown here, and if you were to subtract these two values, you have the stroke volume, and it's depicted as the width of the pressure volume loop. Are you all tracking with me still? Okay. Now let's say there's a mutation, right? And we will talk about an example of a mutation in the case of dilated cardiomyopathy, and that's going to make the cardiac muscle less sensitive to calcium, and it's going to decrease the amount of force which is produced. So let's say there's a mutation, and so you have a decrease in the peak pressure. Do you think it will affect the stroke volume? Yes? No? If the peak pressure is decreased, do you think stroke volume will be affected? Yes, absolutely. Notice that less blood will be pumped out and the peak pressure drops, and so the stroke volume decreases. And you'll see the stroke volume decreasing is also shown in the pressure volume loop as well. Now there is something known as ejection fraction, which can be calculated using all of these values, and this is the percentage of end diastolic volume represented by the stroke volume. So if you want to calculate ejection fraction, you will take the stroke volume, divide that by the end diastolic volume, multiply that by 100, and you will get the ejection fraction. Are we clear? Yes. Okay. So now let's look at a couple of terms which I will hold you responsible for, right? We're going to look at three terms: preload, afterload, contractility, and let's see what they are. So we see that preload is defined as the stretch of the myocardium, and the stretch of the myocardium can also be considered as the end diastolic volume of the ventricles. So I told you diastole is when the ventricles relax, and at the end of this relaxation, the volume of blood in the ventricles will indicate how much it's been stretched, and so that is the preload. Okay, and then the afterload is the force against which the heart has to contract in order to eject the blood. So you see that in the isovolumic contraction, the heart is contracting, but no blood is being ejected because it has to exceed the aortic pressure, and that aortic pressure is the other term for the afterload. This is the load against which the ventricle has to contract in order to eject the blood. Now the third term I will introduce to you is called contractility. Right? So this is the relative ability of the heart to eject a stroke volume at a given prevailing afterload and at a preload. So this is just referring to what is the force which can be generated by the heart muscle when it's at a given length against a specific afterload. So this is what is contractility. Amount of force generated at a given length. So now let's walk through the various steps of the pressure volume loop. I told you how this is made, but let me just tell you what's happening in the heart at each point of this pressure volume loop. So in this figure, we're going to start by considering that pressure shown on the y-axis, volume on the x-axis, and this is the point where you have the end systolic volume, right? All the blood has been ejected from the ventricles, and most of the blood has been ejected from the ventricles, not all of it. And we see that when the ventricular pressure drops below the atrial pressure, there is the opening of the mitral valve. So this is on the left ventricle. On the right ventricle, you will have the tricuspid valve opening. So the atrioventricular valves open, and then you have blood flowing from the atria into the ventricles passively, and so the volume gradually increases until it reaches the point of the end diastolic volume. So the ventricle is completely relaxed and it's filled with the maximum amount of blood. And this is going to represent the preload. At this point, you have the QRS complex causing ventricular depolarization, and then you will have the systole beginning at this point. And in this systole, the first part is the isovolumic contraction, where the ventricular pressure is still below the aortic pressure, and then once it exceeds that, we see the opening of the aortic valve and blood is being ejected out. And as blood is ejected, notice that the volume is gradually decreasing. Right? It gradually decreases until the ventricular pressure drops below the aortic pressure, and the aortic valve will close. Right? And then this will be followed by a time of isovolumic relaxation. And the width of this PV loop is representing the stroke volume. So all of this we have talked about in the previous slide, and I just repeated it so that more repetition is always better. The one thing which we haven't seen before is this slope here, right? What is the slope referring to? So this slope is reflecting inotropy. Right? Inotropy means ino refers to muscle or fiber, tropy means to turn on. So it's going to refer to the contractility which we discussed in the previous slide. So this is the amount of force which can be produced by a given muscle at a given length. And in the clinical setting, when they measure these pressure volume loops, they can look at this slope and indicate what is the contractility of the heart. Right? So if you notice in this figure here, this red color slope is going to be steeper compared to this black dotted line slope. So the steeper this slope is, it indicates as higher contractility, and the heart can produce greater amount of force. And that is the reason why if you compare the stroke volume of this red loop versus the black loop, it has a greater stroke volume. So it has ejected more blood out because it has a higher contractility. Are we clear on that? How the pressure volume loop can indicate what is the contractility at a given length. Alright, so if there are no questions at all, we can move on to what are the factors which affect cardiac output. So the cardiac output is defined as the volume of blood which is pumped by the heart in 1 minute, right? And this will indicate how effective the heart is as a pump. So if it's going to pump out a lot more blood in a given minute, then it is more effective. Now there are two factors which influence this cardiac output. The first one is the heart rate, which is the number of beats per minute, and also the stroke volume, which is the ml of blood pumped per beat. Right? And so if you multiply these two, you come up with the stroke volume. And on average, stroke volume is, when you multiply these two, you get the cardiac output. And on an average, our cardiac output is around 6 liters per minute, because you have 80 ml per beat and you have 75 beats per minute. So if you multiply the two, you get 6 liters per minute. And we already know that stroke volume is determined by the difference between the end diastolic volume and the end systolic volume. So if you have a great amount of end diastolic volume, it will increase the stroke volume, and the lesser the end systolic volume, the less the amount of blood is remaining in the ventricle after the contraction. That indicates higher stroke volume has been pumped out. So we find that the heart rate, on the other hand, is influenced not only by the autonomic innervation, we'll talk about this in a few minutes, but also depends on what type of hormones are released. Right? If you have epinephrine, norepinephrine released, it can increase the heart rate. So for the next few minutes, we'll talk about what are the factors which change stroke volume, and basically it's just the change in muscle length, and then we'll move on to how the heart rate can be affected as well. So we see that as you are exercising strenuously, depending on the individual and the amount of training, your cardiac output can increase by 4 to 7 fold. And the amount of blood which is pumped from the ventricle is normally determined by the venous return. Right? What do we mean by venous return? So it just indicates how much blood is going to be brought to the atria by the various veins. So do you know what veins bring blood to the left side of the heart versus the right side of the heart? talked about this in part 1. What are the veins which bring blood on the right versus left? What blood vessels bring blood to the right versus the left side of the heart? You're talking about venous return, yes?
The cava for the right, inferior and
inferior and superior vena cava for the right, and for the left?
the pulmonary veins.
Pulmonary veins. Excellent. Thank you very much. So this is showing you that depending on how much blood comes, it can influence how much is going to be pumped up. So we find that there's a principle known as the Frank-Starling principle, and this indicates that if you have more blood coming to the heart, more will be pumped up. And this is similar to how a rubber band works, right? If you were to stretch a rubber band more, it's going to bounce back with greater force, and that's sort of how this Frank-Starling law is indicating. The more blood entering the heart, the more it's going to be pumped up. But the mechanism underlying this, we know it's not because the heart wall is like a rubber band, but rather it's indicating how much interaction between the actin and myosin filaments will take place. So this is a figure we looked at previously. Shown on the y-axis, we have the force response for changes in muscle length on the x-axis. So notice that as you go from this point A to point P, you have a very dramatic increase in force, even for a small change in muscle length. Whereas after you reach this, when you go from B to C, there's only a slight change in muscle length, and then from D to E onwards, any further increases decreases the force produced. And the reason is, between A to D, the more you increase the muscle length, you are going to have more overlap between the thick and thin filaments, which means there will be more actin myosin interaction, and so it will produce more force. Going beyond the optimal length means that you have less overlap, which means less actin myosin interaction and less force generated as a consequence. Now the cardiac muscle will be in this ascending limb physiologically, and so even smaller changes will lead to smaller changes in muscle length will lead to greater changes in the force generated. So in this figure, I told you that the normalized forces are shown on the y-axis, and the reason we need to see the normalized forces for cardiac versus skeletal muscles is that cardiac muscles produce much less force compared to the skeletal muscles. So comparing the normalized forces will help us to understand how the force will change based on changes in muscle length. So in the physiological range, in the cardiac muscle, if you have around a 10% change in muscle length, you have around a 50% increase in force generated, whereas a 10% increase in skeletal muscle length will lead to around only 15% increase in force generated. And so we find that the more blood is returned to the ventricle, it means there will be a larger stretch of the ventricular muscle, and as a result it's going to have a stronger contraction because you have more actin myosin interaction generating more force. And as a disclaimer and a side note, notice that any sort of overstretching by the cardiac muscle will be prevented because of the connective tissues which hold the cardiac myocytes in place. So now let's talk about a pathology known as cardiomyopathy, and I want to talk to you about two types of cardiomyopathy. We talk about hypertrophic and dilated cardiomyopathy. So in hypertrophic cardiomyopathy, notice that the ventricular walls, they're going to get greatly thickened and it enlarges. And hypertrophy is something which athletes trying to accomplish because when you exercise the muscle more, the fibers get bigger, and that's what you're trying to do, right? You want to increase the load so that the muscles hypertrophy. But in this type of hypertrophic cardiomyopathy, you have some type of mutation which can increase the calcium sensitivity of the muscle fibers. So for a given amount of calcium, these fibers will produce greater amount of force, right? That's why it's like they're constantly being exercised and the walls will thicken. And the problem with this is that in normal athletes, they're not exercising all the time, they're only exercising maybe a few hours a day, and that leads to this type of hypertrophy, which is normal, but when you have a mutation which increases the calcium sensitivity constantly, the remodeling can be pathological, and I'll explain why it is pathological in a minute. On the other hand, if you have a mutation which is going to decrease the calcium sensitivity, the cardiac walls can develop this dilated cardiomyopathy. Right? So let's walk through this. Let's say if you have less calcium sensitivity, what do you think will happen to the force produced by the ventricles? Will it be increased or decreased? Less calcium sensitivity, the force generated by the ventricles will decrease. Thank you. Now, if the force generated by the ventricle decreases, what do you think will happen to the stroke volume? Would it increase or decrease? The stroke volume decreases, right? What would happen to the end systolic volume? End systolic volume will increase or decrease when you have low calcium sensitivity. You have less blood pumped out, so the amount of blood remaining in the ventricle will increase, right? If enough blood isn't being pumped out, the end systolic volume will increase. Now, for the next beat, more blood comes in, right? What do you think will happen to the ventricular walls? You already didn't have enough blood pumped out, and you have so much remaining, and more blood is coming in. What will happen to the ventricular walls? It's going to stretch even to a greater extent, right? And so the preload in the ventricles will increase because in the previous beat, not sufficient blood was pumped out. Are we tracking? Are you tracking with me? Yes.
Does that ever lead to like ruptures of the wall?
No, not at this point. Yeah. So we find that the preload keeps increasing, and when the preload increases, the Frank starting mechanism is going to be triggered, and so the ventricle will pump out blood with greater force. And we find that constantly the ventricle is forced to work at a longer length, right? And by constantly working at a longer length, we find that can be pathological remodeling. So whether the walls hypertrophy or they dilate and get thin, the conduction system is going to be messed up, right? The conduction system, which is made up of 1% of the autorhythmic cells, that signaling network can be messed up, and that can lead to arrhythmias, and it can even cause sudden cardiac death. So there have been cases of athletes, elite athletes, in the middle of a sport, they suddenly drop down dead because there could have been this type of pathological remodeling. And when you have an arrhythmia, it's going to be, you can have a cardiac arrest, and it can lead to instantaneous death. So before we move on, I just wanted to tell you that there can be problems in the heart for multiple reasons, right? We looked at a few of them. We looked at how clogging the vessels can lead to heart attack, electrical signals being dysregulated can lead to arrhythmias, and that is cardiac arrest. And we finally talked about cardiomyopathy, where you have abnormal force generation, whether you have too much or too little on a constant basis, that can lead to dilated or hypertrophic cardiomyopathy, depending on whether you have higher or lower calcium sensitivity. Is that clear, folks? There are other problems we can talk about, like problems with the valves, and there are a lot of things which can go wrong. Right? I'll give you 3 examples of pathology. So now let's move on to the autonomic innervation of the heart. So we find that there are these cardiac control centers in the medulla oblongata, it is the brain stem, and there will be receptors to monitor changes in oxygen and carbon dioxide concentration. Those are chemoreceptors. There will also be baroreceptors which can detect changes in blood pressure, and accordingly you can have either the parasympathetic system or the sympathetic system being activated. So shown here in blue is the cardioinhibitory center, which will be activated during parasympathetic stimulation. And notice that the neurons, they will pass through the vagus nerve, and it will eventually reach this cardiac plexus, where the pre-ganglionic fiber is going to synapse with the post-ganglionic fiber. And this innervation will not only go to the atrioventricular node and the sinoatrial node, but there's also some parasympathetic innervation of the ventricular walls as well. And the way the parasympathetic stimulation can cause relaxation of the heart is by slowing down the heart rate, and it does that by causing hyperpolarization of the membrane potential of the autorhythmic cells. And you'll see that acetylcholine, which is released by these parasympathetic neurons, it will cause the outflow of potassium ions. So by opening these potassium channels, it's going to cause a greater hyperpolarization, and that can decrease the heart rate. How this works, we will consider in the next slide. But alongside the cardio inhibitory center, we have the cardio accelerator center. Notice that these neurons, they pass down to the spinal cord, and from there you have these preganglionic fibers synapsing with the postganglionic fibers, and eventually it moves through the cardiac nerve. And there's not only innervation in the sinoatrial node and the atrioventricular node, but there's also sympathetic innervation of the ventricular walls. Now, the sympathetic innervation of the ventricular walls will be more than the parasympathetic innervation of the ventricular walls. And the way the sympathetic system can increase the heart rate is by causing the membrane potential of these autorhythmic cells to depolarize. And it does that by opening two types of channels. It opens both sodium and calcium channels. Right? So let's see how the opening of different types of channels can either slow the heart rate or make it go faster. So in this figure here, notice that the membrane potential is shown on the y-axis, and on the x-axis we have the time stamp. And acetylcholine, which is released during the parasympathetic stimulation, it will cause the opening of potassium channels. And the question I have for you is, do you remember what causes this slow depolarization? We talked about this. Yes, what causes slow depolarization? No, the slow depolarization here to reach a threshold. What causes that? I talked about some fine currents, right? Yes.
Isn't that going to be the opening of ligand-gated sodium channels?
It is sodium channels, but it is ligand-gated. So the cyclic AMP binding and the hyperpolarization, the HCN channels, they are the ones which will cause this slow depolarization to reach the threshold. Once the threshold is reached, what causes this rapid depolarization? It's a voltage-gated.
Is that calcium?
Yes, voltage-gated calcium channels cause the rapid depolarization, and this repolarization is caused by potassium channels, right? So this acetylcholine is going to cause those potassium channels to open, and so we'll have a greater amount of hyperpolarization. And the greater the hyperpolarization is going to take a longer time to reach this threshold through the HCN channels, and that's why the heart rate is going to be decreased. Is that clear, folks? Why acetylcholine is causing greater hyperpolarization? It acts on the potassium channels. Now, on the other hand, during sympathetic stimulation, we have norepinephrine released by sympathetic neurons, and that causes the opening of both the sodium channels, which causes this threshold to be reached, and it also causes the opening of the calcium channels, which causes this rapid depolarization, right? And so we find that that the depolarization is going to be reduced, and so this threshold can be reached pretty quickly, and as a result, the heart rate is being increased. Are we clear? All right, fantastic. So we find that during the fight or flight response, there will be increases in the contractility of the cardiac muscle. It means it's going to produce more force at a given length, and as a result, the amount of blood being pumped out will be increased as well. And the peripheral blood vessels, they will be constricted, right? So during this sympathetic activation, the blood flow to peripheral organs like your fingers and toes, that will be decreased. That's why you can get really cold hands and feet. Instead, the blood flow will be directed to the larger organs to the heart and to bigger muscles to run away, right, from something which is chasing you. And because the heart rate has been increased, there will be 2 to 3-fold increase in the overall cardiac output. And depending on the age of an individual, in young adults, it can even reach from 70 beats per minute to, it can increase from 70 beats per minute to even 200 beats per minute in young adults. Now, in contrast to the peripheral blood vessels, the bronchioles, right, they also have smooth muscles, but they are going to dilate so that more oxygen can enter into the respiratory system, and we'll see how this functions in the respiratory system. So with that, we'll move on to the concept of how blood flow can be influenced by 3 different factors. The resistance is referring to the opposition in the blood flow, and the 3 factors we consider are blood viscosity, vessel length, and the radius of the vessel as well. Okay. So blood viscosity is determined by the number of formed elements. So we'll see water formed elements, and can even be influenced by the diet as well. So higher the viscosity, there's a greater resistance to the flow of blood. And longer the blood vessels, it's going to be increasing the resistance as well, right? So if you were to try to drink out of a straw which is like 10 times the length of a shorter straw, you're going to put a lot more pressure in trying to make that liquid reach your mouth, right? So the longer the blood vessels, greater the resistance. And in tissues like fats, you have a lot fewer blood vessels. You have around 200 miles in a pound of fat of blood vessels, whereas a pound of muscle would have over 400 miles of blood vessels, because those muscles are having a higher energy demand. And the diameter, the larger the diameter, the less the resistance, because the more the fluid is in contact with the walls of the vessel, there's greater friction, and that's going to increase the resistance. But if you have a greater diameter, the contact of the fluid with the walls of the vessel decreases, and that can decrease the overall friction experienced by the fluid. So as we go from the aorta, which is pumping the blood from the heart, down to the vena cava, which is eventually bringing the deoxygenated blood back to the heart, we find that the blood pressure is going to gradually decrease. Right? And we see that one of the steepest drops in the blood pressure is in the capillaries, and that's where you're going to have exchange of nutrients and gases and waste taking place. Right? So we'll talk about what is so unique about these different types of blood vessels. So in this figure here, notice that there are different types of arteries. You have elastic arteries, which have a greater diameter, muscular arteries, which have a smaller diameter than that, and finally you have arterioles, and arterioles can give rise to the blood capillaries. On the other hand, we have the large veins, which have a greater diameter compared to these muscular veins, and then the venules, they'll have a smaller diameter, and eventually that can lead to the capillaries as well. The purpose of showing you this slide is that the diameter of these vessels changes, as they start branching, and they're going to get smaller as they branch more and more. But there are a couple of things that I do want to point out about the arteries and veins. What are some major differences? So the similarities between arteries and veins is that they have 3 layers, right? And the outermost layer is called the tunica externa. It's made up of connective tissue. Tunica media is the middle layer. It's made up of smooth muscles, and then the tunica intima is the innermost layer of the blood vessel, and that's got 2 parts. It's got this basement membrane, and then it has the endothelial layer, which is actually in contact with the blood which is flowing through. Right, so you have these 3 layers both in arteries and in veins, but one of the major differences is that the tunica media is going to be very thick in the arteries. Right? It's thicker because it's going to resist more higher pressures. Right? So it has to be thicker. And Because the veins have less of the tunica media, the walls will be pretty floppy and flattened. Right? They won't be firm and circular. And another difference we'll find between the arteries and veins is that veins will have valves to prevent the backflow. Right? And before we move ahead, I'll just mention a side point. We'll see what changes happen to this endothelial layer when we talk about plaque buildup. Right? When we have atherosclerotic plaque buildup, it's going to start with changes of this endothelial layer, and the mechanisms of that will concern the digestive system. But now let's move on to talk about the valves which are found in veins. And the purpose of these valves is to prevent the backflow of blood. So notice that these valves are going to open this way, and so blood can flow from the bottom straight up to the inferior vena cava, and when the blood pressure drops, they're going to collapse on itself so that blood can flow back down again. And as we age, these valves can be weakened and they can get stretched, and so it can lead to a condition known as varicose veins. Where there can be pooling of blood in these veins because of the damaged valves. And so with that, we'll move on to how the blood flow can differ between these different types of blood vessels. And we'll see the relationship among vessels in the systemic circuit. So there are 4 graphs we'll go through, right? And let me walk you through each of those one by one. So the first graph is showing you the vessel diameter on the y-axis, and you see the names of the various vessels. And you notice that the arteries, they're going to have a greater diameter than the capillaries. And as you go from capillaries to the veins will have a higher diameter. In the second panel, we'll see the total cross-sectional area, right? So the elastic arteries have a lower cross-sectional area compared to the capillaries because the number of capillaries are just so many more. So even though individual capillaries have a smaller diameter, we just have more number of capillaries, so the collective cross-sectional area is higher. And in the third panel, we have the blood pressure shown on the y-axis, and on the x-axis we see the various blood vessels, and this is a picture we saw previously. As you go from the elastic arteries down to the vena cava, there will be a dramatic decrease in blood pressure. And finally, we see that the velocity of blood flow is going to decrease as you go from the arteries down to the capillaries, but then you see from the capillaries onwards there's a gradual increase in the velocity with which the blood flows. And the reason for that I'll explain in a minute. So let's start by talking about the first 2 graphs. We find that the diameter of an individual capillary is significantly smaller, as you can see right here, when you compare it with either the arteries or the veins. But because you have a lot more of these capillaries, we find that the overall cross-sectional area of the capillaries will be much higher than the arteries and veins. Are we clear on that? Why the cross-sectional area of the capillaries is higher? Because you have more number of capillaries. Moving on to the last 2 panels, we see that the greatest drop, in the blood pressure is when you move from the arterioles into the capillaries, right? So that's where you have one of the most precipitous drops in blood pressure. And by decreasing the blood pressure in the capillaries, we see that that is going to permit greater amount of exchange between the capillaries and the surrounding tissue. So the capillaries, where you have exchange of gases like oxygen, carbon dioxide, nutrients, and so you want to have the blood flowing through at a much slower rate to maximize this exchange. And then the last question was, why does the velocity of blood flow increase from the capillaries to the veins? Right? And the reason for this increase in velocity flow is that they're moving from a region of higher cross-sectional area down to a region of lower cross-sectional area, and that's why you have a higher velocity of blood flow from the capillaries to the veins. Yes?
There's also a smooth muscle lining veins that also helps increase blood pressure?
Yeah, that will also play a role, but the difference in cross-sectional area plays a huge role. Alright, so with that, we move on to summarize what we've discussed till now. We talked about how the pressure volume loop is constructed using the various steps in the cardiac cycle. And the pressure volume loop is going to indicate how contractility can change on based on muscle length. Right? So if you have the muscle length increasing, it's going to make the muscle produce more force because you have greater actin myosin interaction due to the greater overlap between thick and thin filaments. And then we talked about the cardiac output being influenced not only by stroke volume but by also by the heart rate being altered as well. Right? So in order to alter the heart rate, we found that the autonomic nervous system was playing an important role. The release of acetylcholine in the target tissue will cause the hyperpolarization of the membrane potential in autorhythmic cells, causing the heart rate to decrease, whereas epinephrine would cause the depolarization by opening calcium and sodium channels as well. We looked at some of the key differences between arteries and veins, seeing that the vessel diameter was greater in the veins, and we found also how the pressure is going to drop as you go from arteries to the veins. But we find that the cross-sectional area of the capillaries is much higher because there are more capillaries than either veins or arteries, and that's why when you go from the region of higher cross-sectional area to the region of a lower cross-sectional area, the rate of blood flow will increase as the blood flows from capillaries to the veins. So with that, we end class today, but let me just make a couple of announcements. So when we come back on Wednesday, we'll go through some of the key questions, actually through all the key questions in parts 1 to 3 of the cardiovascular system. And we'll also do the pole everywhere questions from the muscular system, right? So we'll do that on Wednesday. And once we wrap that, we'll move on to the respiratory system. Thank you all for your time.